confusions actually. I mean, if you ask from them, I have seen that quite often they are confused in all these, all these things, and it's just because that they have kind of ignored tradition as a tradition. They have kind of ignored all these things actually. But when you see things in the context, they seem beautiful. They look good. Okay. So further on, we are also not going to write all these, but we have to keep in our head that this order, so this placement of indices is also telling you something about the bases actually. So they are there for a reason. They are not there for no reason actually. They are telling you something. So you call these are the contravariant components, or these are the covariant components, but that why they are contravariant and covariant is just because of these basis vectors actually, which are sitting kind of silently with them. Okay? Is it making sense? So I hope that you get some bigger picture of what tensors are, at least with regards to definitions. So now you'll see a map, you can easily recognize that, okay, so this kind of a tensor, so that kind of a tensor, so you can make sense of it. Okay? We still have 10 minutes. So what I'm going to do now, so with all these things in our head, let's attack chapter 2 of the book. And you will see that now everything would be, you will see, okay. Everything will make sense to you. Everything. Shall I get rid of it? So the chapter 2 is on differential forms. I mean, in principle, the chapter 2 that we are doing is not really differential geometry, it's something independent, but it's a language in which we are going to express the rest of the things of differential geometry, so it's pretty important to make sense of that language. Okay? So we don't have a vector space here. Okay? So when we begin, for us vector space is what? Here, in this context, in the differential geometry context. So for us, vectors are tangent vectors actually, attached to some point, having some Euclidean part attached to it. So, and collection of all such vectors is? So this is collection of all tangent vectors actually. Okay? And we know that the basis of this tangent space is partial by partial x1, partial by partial x2, and partial by partial x3 actually, yeah? x3, oh yes. So if I put an Rn here, it's partial by partial xn actually. And everything evaluated at a point. Huh? Everything you have to do these evaluations at a point actually. So we know that. Okay? And I gave you an exercise that proved that this is a basis for such kind of a map. I don't know that whether you have attempted or not. If not, my sympathies are with you. Okay? So what would be the dual to such kind of a maps actually? So what would be TPM and its dual? So this is going to be the collection of the covectors. Okay, so the collection of the linear. So it's a collection of alphas such that alpha from alpha from TPM to R is our linear maps actually. Okay? Just linear map. And now I can know that this linear map is what? It's a 1-0 tensor for me. Okay? And P, I also call such linear maps as one forms. Okay? What do you call them? One forms. So that's my one form. So whenever I mean a one form, I mean a linear map from tangent space into the R. Okay? And I know that my one forms are 1-0 tensors as well. Okay? We give this guy a particular name. We call this as this is the cotangent space actually. Cotangent space at a point P in R3. Okay? And the union of cotangent spaces, okay, P is a point in R3. What name should we give it? What do you think? So if these guys are cotangent spaces,
Cotangent bundles.
so it should be cotangent bundle. It's a cotangent. Okay? Cotangent bundle. Just a simple notation. Would be an interesting question, what is the basis of this? We want such a basis that has that chronicle delta relationship with this actually, with the basis of what we call the cotangent space. So we're gonna get to it. Now let's do a miracle. It's really a miracle. And the miracle is, so you see, the notion of differential that you have in calculus actually. So you learned a whole lot of kind of differentials and derivatives and all kind of things. But at the heart of all this, there is something which is, so how do we understand differentials? So it's like in Newtonian way, if you want to understand them, so they are actually, what do you call, the infinitesimals actually. Well, the question is, what is infinitesimal? Okay. So analysis, okay, so it's like we learned that, okay, if you can think of something smallest, these things are smallest than that. Okay. If you can think of something smallest, they are smallest than that. Okay, it's good, but it's still not precise actually. So what we are going to do, we'll see that we are going to see or take or define the differential forms as one forms actually. Sorry, differentials as one forms. So in other words, these are linear maps. So if these are linear maps, think about it. There's a whole rich theory of linear algebra is sitting at the behind. You know everything about them. So it's like, think about it. So if you treat differential as something linear, okay, then you are not talking about something vague. So linear things has a very precise definition actually. So not only they have a precise definition, they have precise description. You have theorems in linear algebra, giving hell lot of information about, all those, what do you call, linear maps actually. So if we start seeing, differentials, linear algebraically is going to make our life easy, much more easier. And this is what essentially we want to do. So we want to kind of algebraize the calculus. Okay, this is what essentially we want to do. Okay, so here's the definition, quickly. Here's the definition, quickly. Okay, so the P is a point in Rn. Okay, and TPRn is a tangent space. Okay, so we defined one form already. So Rn is tangent space. By a one form, I mean a map phi.
Tangent space.
Okay,
Linear.
this is a map from TPRn into R such that huh? What do you mean by
Like we are three.
RN? Sorry, RN. Everything is at least we can define things abstractly. We can see them in then R3 and R4. So one form is a map such that it takes two tangent vectors, for example xp, yp, and we know we define such notions. Okay? And it gives you what?
Phi of
So
xp
phi of
plus
xp
plus phi of yp.
phi of
yp.
yp.
And this scale.
And have phi of, if you scale down a tangent vector, the image will also be scaled up. So this is what do we mean by one format. Okay? Now, you also remember so let me define next differential. So we define differential of what? So we define differential of a scalar field. So let f be a scalar field. So let f from Rn to R PC infinity. Okay. Then we define differential as an operator. Okay. So I'm defining the differential of f as an operator. So operator is doing what? It's taking a vector field. Okay. It's taking input as a vector field and giving me all the possible directional derivatives of, okay, so it's like at f actually, so x of f. Remember x of f we defined it in the last time? Okay. So this is what essentially my definition is. That I'm defining, how I'm defining differential. The differential is a kind of a linear map that swallows a vector field. Okay, and then it gives what? So it takes the f and create what do you call? So it's like takes the tangent vector at each point on that f. Okay, and give you what do you call this? This version of a vector field. Some version of what are it? It's a version of directional derivative. If you see it on a particular tangent vector actually, so it's like we can see it more explicitly. We can make more sense of it. Okay. Let's so differential, and I'm applying it on maybe some xp, some tangent vector. So xp is what? So it's just a realization. So it's like a vector field at a, so it's like a value of the vector field at a point P. Okay. This is just going to give me a tangent vector. So it should give me what? So it should give you xp operated onto f. But this is what? This is directional derivative. So what does it mean? So it's like compute the gradient of f, evaluate at p, and compute dot product is with x. Okay? And the x, this small x is what? It's a Euclidean vector attached to the point P. Okay? And obviously you have to see it as this is what you're gonna get. Are you getting the point? Now here's the interesting thing. What if I take a particular scalar field that is coordinate maps, and consider the differential of it. So this is also going to swallow such kind of tangent vectors and give you some numbers. What if I give them a particular kind of a tangent vector, not general kind of a tangent vector, but a particular kind of a tangent vector, and that tangent vectors are basically these, the bases of the tangent space. So in other words, what if I give them partial x by partial xj and everything evaluated at point P? What do you think? What are you going to get? Kronecker delta, but how? Can I use this definition? So this would be same as partial xi xj. That's it. And this would be same as delta. Is it giving you kind of a thing? So this is what? Basis for the tangent space. What do you think? What would be the basis for the cotangent space? So it must be spanned by these particular one forms. Okay, these differentials actually. So it's like dx1 up to dxn. Verify this claim that this is indeed a basis actually. And it's not only a basis, but this is a dual basis. Because if you have a basis which satisfies such a relationship, okay, so it's like, what was the relationship between EI and epsilon j? So it was delta ij. And then we say that, okay, these epsilon i's are basically a dual basis to V star, okay, of the basis this one. It is a dual basis. So in other words, this is also a kind of a, so these differentials of coordinate maps are kind of the dual basis for the vector space V actually. For the cotangent space at a point. Are you getting the point? Try to verify it. I think it's enough for today. We're going to do this again next in the next discussion. Okay, and like start from here, and then okay, we'll try to